Welcome to Lesson 8 of Applied Physics. This lesson covers drawing linear motion diagrams. In this lesson, you will cover the following objectives. Differentiate between the concepts of position, velocity, and acceleration. Recognize the relationship between velocity and acceleration when an object is speeding up, slowing down, or turning. Interpret kinematic graphs and to relate position, velocity, and acceleration graphs to each other. Begin the development of a robust problem-solving strategy. And solve quantitative kinematics problems, including objects falling under the influence of gravity. Take a moment to study the four equations listed here, which are called the kinematics equations. The terms associated with these equations are defined as well. One of the tools that can be used to help visualize and understand motion is the motion diagram. There is no elaborate art involved here. It is simply a sketch. The moving object can be represented by a dot. The motion diagram shows the position of the object as it moves over time. There is equal time between each object position in the diagram shown here. You can think of it as a stroboscopic picture. A stroboscope is a light source that flashes on and off periodically. Imagine that the object is in the dark except for the strobe. Every time the light flashes on, you can see the object's position. The time between flashes is always the same, and the path of the motion will be recorded. This represents a motion diagram for a car moving to the right. The diagram starts at time equals 0 seconds, when the car is at position 3 meters. It continues at regular time intervals until the car is at position 11 meters. Watch this example showing a man moving with constant velocity motion. You can picture any constant velocity motion in this way. A motion diagram represents the position, velocity, and acceleration of an object at several different times. The times are usually separated by equal time intervals. At each position, the object's velocity and acceleration are represented by arrows. If the acceleration is constant throughout the motion, one arrow can represent the acceleration at all positions shown on the diagram. We will be drawing motion diagrams of constant acceleration or for regions of constant acceleration. Take a moment to read more on drawing motion diagrams. The first motion diagram, shown in Figure 1, is for an object moving at a constant speed toward the right. The motion diagram might represent the changing position of a car moving at constant speed along a straight highway. Each object indicates the position of the object at a different time. The objects are separated by equal time intervals. Because the object moves at a constant speed, the displacements from one object to the next are of equal length. The velocity of the object at each position is represented by an arrow with the symbol V under it. The velocity arrows are of equal length and in the same direction. The acceleration is 0 because the velocity does not change. The motion diagram in Figure 2 represents an object that undergoes constant acceleration toward the right in the same direction as the initial velocity. This occurs when your car accelerates to pass another car or when a race car accelerates or speeds up while traveling along the track. Once again, the objects represent schematically the positions of the object at times separated by equal time intervals at delta t. Because the object accelerates toward the right, its velocity arrows increase in length toward the right as time passes. This product, A delta t equals delta v, represents the increase in length or the increase in speed of the velocity arrow in each time interval delta t. The displacement between adjacent positions increases as the object moves right because the object moves faster as it travels right. The motion diagram in Figure 3 represents an object that undergoes constant acceleration opposite the direction of the initial velocity. This is sometimes called deacceleration, a slowing of the motion. For this case, the acceleration arrow points left opposite the direction of motion. This type of motion occurs when a car skids to a stop. The objects or cards represent schematically the positions of the object at equal time intervals. Because the acceleration points left opposite the motion, the object's velocity arrows decrease by the same amount from one position to the next. We are now subtracting delta v equals a times delta t from the velocity during each time interval delta t. Delta represents the term change, so read this as change in velocity and change in time. Because the object moves slower as it travels right, the displacement between adjacent positions decreases as the object moves right. This implies that the acceleration is in the opposite direction to the direction of the velocity. You should become so familiar with these motion diagrams that you can read a linear motion problem and draw a reasonable diagram that represents the motion described in the problem. The following website shows examples of animated motion diagrams. Here is an additional example of 3 animations which show constant velocity and constant acceleration. Let's try a problem. On your own, draw the motion diagram associated with the problem as you do it. Starting from rest, a car accelerates at a constant 4 meters per second squared for a distance of 425 meters. The car is then shifted into neutral and slows down at a rate of 2.25 meters per second squared. How much time elapses between when the car starts and when it stops? Which of these motion diagrams would correspond to the problem statement? Actually, case 2 and case 3 are correct. Case 2 shows the acceleration for the first 425 meters, and case 3 shows it for the last part of the stopping motion. Try another problem. On your own, draw the motion diagram associated with the problem as you do it. A hot air balloon is rising upward with a constant speed of 3.5 meters per second. When the balloon is 115 meters above the ground, a passenger trying to take a picture accidentally drops his cell phone over the side of the balloon. Ignoring air resistance, how much time elapses before the cell phone hits the ground? This is only part of the motion diagram necessary to solve this problem. What about the initial motion of the camera still moving up after the camera is dropped? This is only after the camera stops moving upward and is only falling downward. Can you determine the type of motion shown here? Take a minute to review these essential equations for kinematics. One question that oftentimes arises is what is the difference between displacement and distance? One is a vector and one is a scalar quantity. View the following animation and see if you understand the difference. A car with a non-zero initial speed has a constant acceleration whose value can be controlled by the user. Use this animation and study the effect of changing accelerations on a car. You should also note the graphs that are being drawn in the illustrations, as these graphs can be very helpful tools in solving basic kinematic problems. Remember that kinematics is the study of the description of motion, and a good physics student will be able to read the words in a problem and will be able to represent the words in drawings, i.e. motion diagrams, graphs, and using equations. These pages and simulations are here to assist you in experiments which can help you gain a better understanding of the descriptive terms, pictures, charts, and equations which are used in this area of the science. One-dimensional kinematics of a body undergoing constant acceleration includes visually integrating the acceleration and velocity graphs and visually differentiating the position and velocity graphs. Again, this is another example with greater details of how kinematic graphs can represent words, motion diagrams, and graphs, which will eventually lead to either linear or some other functional representation as a mathematical equation. This Java applet shows a car moving with constant acceleration. The green control panel contains text fields where you can vary the values of initial position, initial velocity, and acceleration. The applet shows the motion of the car as well as graphs of x, v, and a. Click the link to see a demonstration. When working on homework problems for this chapter, you might use these computer simulation tools to help you visualize the motion of the textbook or homework problems. This applet shows position, velocity, and acceleration graphs for 6 different scenarios. It also includes an option where you can edit the velocity versus time graph. Click the link to see the example. The PHET site at the University of Colorado has an excellent set of simulations which can help a physics student understand motion. This PHET is called the Moving Man. Click the link to go to the following site. Here you can learn about position, velocity, and acceleration graphs. Move the little man back and forth with the mouse to plot his motion. Set the position, velocity, or acceleration, and let the simulation move the man for you. So, how well do you understand kinematics? Here's a question that has stumped many a physics student in the past. Can you answer it correctly? 2 balls roll down 2 different low-friction tracks near the Earth's surface. The user is invited to predict which ball will reach the end of the track first. The answer is the blue ball. Why? Because the blue ball actually undergoes an acceleration and therefore goes faster than the red ball, even though the blue ball then accelerates negatively at the end. It never has less speed than the red ball at any time. Click on the following link to see the answer, and it should help you with any confusion that may arise. The image on the left shows a standard set of motion diagrams. Can you match the motion diagram with the appropriate position versus time graphs, velocity versus time graphs, and acceleration versus time? Now take some time to bust a move and work the problem sets from your textbook. In this lesson, you covered the following objectives.